Hello everybody. This video is about your third homework assignment. This homework and the next homework 4, will be a teamwork assignment. So you have to first you have to form your team. So therefore you will be using dos.control.itu.edu.tr. Using this website you can create teams, choose your team, and each team will be there is also this is also written down in the PDF, but I wanted to remind you. You're expected to form teams of 3 students using the DOS system, as I've shown you, and there should be a team leader, 2 researchers, and a reporter. Or if you are only 3 students, then this would be 1 team leader, 1 researcher, and 1 reporter. Now, you can also read this paragraph here, but what it essentially tells you is that you have to work in teams. This homework is not only about the theoretical part of our course, this also gives you a good practice in working with teams. So you will each have a role and you will execute that. So you have to communicate in your team if there is, for example, a problem. If you are stuck with a problem solution, then you may, the team leader may have a little meeting, and then you might help each other out. By the way, this teamwork is not only to split it in 3 and then just do your own work. This is just to have a lighter weight in terms of requirements of the homework. So what you have to think about here is that you will do your part, but you have to ask your teammates to explain you the stuff they did. So it should be a collaboration here, and you should be aware of the whole homework. So keep that in mind. Now you will be preparing a report, and therefore you might use this weekly uploaded literature notes as a template. This is a good template. There are questions, and what I am at least doing here is I'm explaining it step by step. Now, for example, there is a p-type controller design problem. There's a system given. So you already have this PDF, by the way. So I define a system. I look for the requirements. There's an overshoot requirement, so I'm using that information to get the zeta value. After that, I form my polynomial. I choose the controller type, and then I form the closed loop and state the problem. And then I have the code. You can skip the code part because in the homeworks we are not really interested in the code you type, because that is pretty obvious that the MATLAB part, I'm really familiar with it. So if there's something different that you've established, for example, most of the time you're familiar with this stuff, but this might be the only point that that someone may be interested in, because this eliminates, for example, the negative values for omega. So if such an occasion occurs, then you might just give 2 lines of code that explains the originality of your code. But other than that, providing MATLAB code or forming only MATLAB code solutions does not work really. And instead of doing that, because this is not really a learning process, this is just copy and paste, the learning process is to form your solution, to write down, to document it. And that's also the aim if you have a midterm exam, if you have a final exam. So think about that. Here we have the solution, and after that we have the validation step, where we have results, the step response, for example, for the system, and then also maybe the root locus plot for the open loop system, which shows that this is the only path that I can achieve to get the zeta value that is given in the question. So that's basically the solution. That's the detail of your report. So if you skip this code part, you have just the basic steps here. Give the system, give some steps that are important, that have meaning, and you have the problem and then the solution. And the solution that you give here is the p-type controller itself, the closed loop, maybe it's also a good idea, if you look at this transfer function, it's not really easy to evaluate what the poles are. So maybe it is also a good option to put in here the pole 0 version here. You might use a ZPK for that. So this equals the coefficient version and then maybe the pole 0 version. It's just a nice touch. So that's it basically. The reporter is the one who should organize this. So for each question there will be a solution, but keep in mind that you should not get lost in the details, just the important steps. If I look through your solution, if someone looks through your solution, they should understand what you're doing, and that's it. So don't overcrowd it, don't just put in the result that has also no meaning. So there's a balance, and try to match that balance. So you can use this as a template, which I'm uploading most of the time, and this is not the only task for the homework solution, or this is not the only file that we request from you. So forming a detailed report, which this is a good template for, is step 1. And step 2 is to create a very summarized and packed version of the solution. So I have prepared the same thing here, just 2 slides, as you can see, just 2 slides. It gives the algorithm, sort of, step by step. The ratio is calculated this. There is this desired polynomial, because this plays an important role in the choice of the solution. So if I choose this different, then I will end up, there's a typo here, I will end up in a different solution. So I give the polynomial that is important, and then I provide a problem, the controller, the closed loop, and then the validation results. That's it. This is pretty easy to prepare, and therefore I will want to show you a little shortcut here in order to help you out in terms of time. So for example, let's try to make Q2. So I have Q2 here, which is the PD type controller. Now I have stated the controller itself, so we might do that too. Let's add a new slide. Let's get rid of this here. Let's get rid of this here. So I'm adding just a text box. You might also use LaTeX if you are familiar with that. That's also okay. So let's say 4, and then just add in. You can add mathematical equations here, and writing mathematical equations are not really that difficult if you know some shortcuts. So for example, so Fs equals k times s plus z. So that's pretty obvious. Now I will not document everything here, but I might just put in, for example, the closed loop. For some reason, yeah. Now the closed loop transfer function is given below. So once I've done that, I'm again adding an equation. Now, if I want to write fractions, I just start to write them, put in a slash, and if you hit space, it will automatically create this fraction for you. And you have k s plus z. Now, if you are writing polynomials, you can just use this shift 3 to generate this here, and if it's s squared, this is s squared. If you hit space, it will just organize it. Now, so we have this here, plus 4k Now that's it. I might also want to give this problem here because it's pretty important. Now I can add again an equation and then a matrix and then this 3-row matrix, for example. And that's basically it. That's also and the corresponding problem. I'm not even completing my sentences, by the way. Is required as follows, for example. So 1 equals 1, and then we have 4k plus 4 equals 1.182. Now, if you want to write omega, for example, you can use omega, a backslash omega and space, and then you have omega. You might also use the plain omega on your keyboard. And if you use underscore and hit space, it will just make it a subscript. And that's it. You don't have to really use the graphical user interface. You can just keep these shortcuts as a cheat set open. Now I want to write omega n squared. So omega squared, for example, is this. And then underscore n. And there we go. So don't get lost in the graphical user interface. Just have some quick tips. For example, if you want to have the you can use these quick tips. If you want to have a square root, for example, as far as I remember, there should be sqrt. So, for example, sqrt 2 and then divided by 2 is square root 2 over 2. So, there are, and if you're familiar with math type or LaTeX, then you might already know these. So therefore, I've practically generated the first part of my solution. I can go on, I can just say the solutions are, and then again, by the way, you can add this here if you use this equation a lot. You can just do that. For example, it is again possible to use this. There we go. Since I have 3 solutions, you can, by the way, click and add here. So there we go. You have mathematical options here you can add. So this does not have to be only 3 rows. So 4, 2, 2, and then -4. You can also add a matrix to organize the stuff here. So there are pretty much options. For example, like that. You can just plug in k here. So it really depends on you, but you can do whatever you want. Or if you have written it already, like me, you can just copy and paste. Once you've created a sort of a template, you can just copy paste and update the numbers. So yeah, obviously. Now then you should give these 2 graphics, and if there's a comment requested, then you might also put that comment there, and that's it. So of course here will be more steps for most of the time, and this PDF is sort of a summarized and compact version. So this PDF will ease up if you the process of grading your homeworks. So it's important that you present your results very compact and create this PowerPoint here. So yeah, that's all about the preparation part of my explanation. Now about the homework itself. There is a transfer function given here, which is parametric. The parameter n0 will be based on your team number. So you will substitute this value for team number. For example, if you are team 20, then n0 should be 20. Now there's also the explanation for that here. As you can see here, group number, team number. So if you are team 5, then you should take n0 as 5. And 6 times n0, an expression like this, will be evaluated 30. So once you plug in your value here, this will end up in a 4th order transfer function with a 0. And the main requirement here is to have a have the second order part or the dominant part to have zeta equals 0.3. By the way, if you use \zeta, then you will get this in PowerPoint, or in Word also, by the way. Yeah, this is the basic requirement. So you have zeta, and the time domain characteristics like settling time, rise time, etc. is up to you. But the important part here is to provide the best solution, and the best solution here is, of course, determined by, for example, the control signal itself and the open loop, for example, settling time. So you should design a applicable closed loop system that meets the requirement 0.3 here. So having like values for poles like 5,000 or 500 will be an overkill. So that's not really the aim here. Or having too slow settling times, for example, like, I don't know, maybe 100-second settling time is not really what we are looking for. So, of course, this is a fourth order system. And when you design a controller to it, this will become even higher of an order closed loop. So keep in mind that this homework is more about the dominant pole placement strategy than choosing the requirements itself. So you might have to adapt your requirements a little bit, maybe a slower settling time, slow rise time. And that's also basically it, what you can do here, which will automatically limit your control signal also. But the aim here is to have a dominant pole placement, but the order is 4 without even a controller. Now, the questions here are pretty straightforward. If you choose a PD controller, what is the best result you can get? So what can the PD controller give me in terms of dominant pole placement? Now here we are not really directly interested in the dominance factor or anything like that, but not directly. Behind the scenes, this will be pretty much important. Now, once you have, for example, tried it with a PD controller, at that point, when you have prepared the report part for B here, and if you have, for example, created this presentation part, like a PowerPoint slide, then you're basically done with your report, because you will be copying and pasting and updating the numbers here. The PI controller, the first order controller, PID controller, PIPD controller have the same sort of algorithm. So this might give you a hint based on the fact that we are asking you to prepare a PowerPoint presentation. Then we can just look at the PowerPoint presentation and see what the PD controller can do, what PI can do, what the first order PID and even the PIPD controller can achieve here. So that's the main skeleton of our homework. Now there's also a method called Ziegler-Nichols oscillation method to come up with PID controller part. This should be fairly easy because it is a very straightforward design method. So you don't have too much control over this. You will just pick the coefficients and get the result. And in A, the question asks for the stabilizing interval of a P-type controller, which should also be straightforward. So the main point here is in B, C, D, E, and F. Now, keep in mind that PD controller, PI controller, PID, and PIPD controllers are kind of the same controller in general. They are under the same family, the PID controller in general. It has a proportional, integral, and derivative part. The PD and PI controllers are kind of a special version of PID, where PIPD is also a special version of PID. So you're designing a PID controller. So keep that in mind. The only requirement is here to have the best, in quotes, solution, and the best solution depends on the dominance factor, depends a little bit on the control signal. We don't know what the system represents in the open loop, so we can't really tell what the settling time should be, rise time should be, or what control signal is really feasible here. But a feeling for it is enough, and an average look at it is also sufficient for us here. So you have to achieve the best controller design in terms of course, dominance factor. Now, as you can see, here's a pattern. So you have PI, PD, PI, first order, PID, and PIPD. Now, this pattern shows you that you have basically an algorithm. You will repeat it over and over again, but there are differences. So what are the differences here? What can PD controller do at its best, and what is the capabilities of the PI controller as its best? Now, keep in mind that having a bad controller here, having the choice not the best, if it's not an optimum solution, then it's not really fair to compare these controllers. So, for example, if you have made a mistake and have a PI controller that really does not a good job, then you might look to your solution and try it again. Because if it's not the best PI we can get, then it's not fair to compare them with the other controllers. So if your solution has its own problems, if it's not sufficient, if you have made a mistake, then you have to correct your answer, basically. But if the controller has some limitations, if you can show that it is the best, then you're okay with it. Sometimes it may not be feasible, sometimes it may give bad results. But if it's really the best controller that can be designed in terms of the structure that is given here, then you should explain that, and that's it. So not always it is not always possible to get controllers like the PI controller should work always. That's not always possible. You have to try your best and explain what is the best here. So, okay, yeah. That's basically it. You have to work with it as a team. You will have your roles. You will use DOST for this, DOST.control.edu.tr. And this report can be based on this template here, without these code bits, of course, because as you can see, the homework itself does not even mention code. So don't provide just code because it has no meaning. And you will be preparing a report that may be based on this, and then also a shorter version, a presentation. And if you are using Word, for example, for your report, you can basically just copy and paste it. So it will hopefully not take that much time. There are some shortcuts in the word processor programs. Maybe you should look at them because it makes life easier. So that's about it for the homework.